Okay, so now that we've watched the simulation, we can write what we see. So we have what we found was that there was what we would call a threshold frequency. This was the minimum energy that was required for electrons to be ejected from the metal surface. So this threshold frequency, we are going to give a frequency and then a little zero or a naught there. And so this was the minimum energy required to eject an electron from the metal surface. Okay, so what that showed was that this light, so electromagnetic radiation, was actually quantized, and so it meant that you couldn't just add, you couldn't increase the intensity of the light to the point in which it kind of summed up to be eject an electron. You'd actually have to have the right frequency of light, and so we have the energy required. We're going to call this our work function. Work function. But it's in joules. That's our unit of energy. And that's equal to Planck's constant H times the threshold frequency. So remember, H is 6.626 times 10 to the negative 34th joules times seconds. And this is work function was specific for a metal. Again, this is looking at ejecting electrons, which tend to happen with metals. So this is a kind of summarizing equation of how the energy required to eject an electron is related to the frequency, but multiplied. Again, the energy is very small. Planck's constant is incredibly small, so it kind of brings that energy down to the microscopic scale. So we can also look at the kinetic energy that came from those electrons, and so we know that the kinetic energy, so the kinetic energy of an electron, so this is kinetic energy of the ejected electron, is equal to the surplus of energy. So you look at, well, how much energy was shown or was radiated at the metal. So that's going to be, this is the energy, this energy from the electromagnetic radiation source. So that would be like the energy coming from this light source right here. And then if you say how much energy, what's the barrier to eject an electron, how much does that cost energetically? And that's going to be the work function times h. And so this equation is, I think, the simplest way to look at it. So this is energy. So this do this in a different way. This would be energy that you have, and this is energy that you need. And the surplus that goes toward kinetic energy is the difference between the two. We can simplify this because we have an h in both cases. Though sometimes we can simplify this to, well, two ways you can simplify it. So I'm just going to write it so you can see. We know that the work function is h times nu, so this could be written as h nu minus the work function. Oh, that's not how you do work function. The work function. That's another way to do it, or sometimes it will be written like this, where you have h, and in parentheses you have the difference in the frequencies. Again, a couple different ways to look at it, but the whole idea is that the work function is the energy. It's an energy barrier to inject an electron. Any additional energy goes to the kinetic energy of the electron. We saw that in the simulation. But the resulting theory, which is very important, that came out of this. So the resulting theory was photons. Okay, So photons can be described in many ways. Mathematically, we can describe it as the energy of a photon is equal to n h nu, where n is a quantum number. It's 0, 1, 2, dot, dot, dot. These are whole integer values. And so this is showing us that the energy, so we have quantization of energy from electromagnetic radiation. That is showing you that we have electromagnetic radiation comes in quantum, and so a way that we can look at that graphically is that we have very similar to what we saw with the emission spectrum of atoms, is that we can have energy level 1, energy level 2. And so if we have, let's say, something, so we can say it's an electron, and we have a energy coming in as electromagnetic radiation, comes in, and it can excite up to an excited state. So this is called absorption, absorbing energy. And so we can get to an excited state. But then we can also have the excited state going back down to the ground state, and a photon of energy would be emitted. So we call this h nu, and this is emission. So it's the emission of a photon, emission of energy back to the ground state, where these are different energy levels. And then let me just do this as well. So this is energy. So photons can be absorbed to put a system in a excited state, and then it can also that can be relaxed back down to the ground state only with the emission of a photon. So photons can be also described as packets of energy. And really, what this is and what came out of this is what we call the duality of light. And that light has properties of both a wave. Now that wasn't surprising. That's how we've described light. And this is what's new, a particle. So a photon is like a particle. So instead of thinking of a wave as being this continuous light, we now think of photons as a discrete packet or a discrete amount of energy. And that for the photoelectric effect, it didn't matter, these could not add up to the total energy you needed. You would need a photon of a given energy to eject an electron. And that's a key finding from the photoelectric effect. This is the real, so in both cases we're seeing this quantization of energy levels within atoms, but now we are specifically giving particle properties to light, which has always historically at that point been treated only as a wave. And so, so we are now treating light as a particle and a wave, and what we're going to find very soon is that we're going to do the same thing with things that we only thought acted like a particle. So matter can actually have wave-like properties as well. So stay tuned for that.